Yeah, I'll have to fix that. That was before I figured out how to use Canvas. Now, not that I really know how to use it now, but I mean, all right, so let's see. That's there. All right. All right, so this guy, oops. That open, yeah. This thing, this thing, this thing. You just need everything here. There's a lot here. Anyway, so we got this paper, which is about so you can hide that. So it's these guys from China. I don't know this place. And Chinese Academy of Sciences sounds good. I don't know this place. So anyway, I don't know these people, but like I think it's a pretty good work, you know. So they're doing a computer simulation to look at how something called tacticity affects persistence. And also they look at the temperature effect thing. So, and they mention in the paper that all the experiments show there's no temperature dependence to persistence, and then the theory says that there should be. This is kind of like 1 over temperature dependence. So like KT, the modulus over KT should be the, and then they say they've explained why that is. And they in the end they say it's because the theories don't include like the density in the melt state, and then if you include the density in the simulation, you can get the temperature dependence to disappear. Because I think because density, thermal expansion, and somehow that impacts resistance. Why it works, they aren't very clear about. Like simulations just do it, I guess, and then you get the answer. And the only difference between their theory and the simulation is that they have density there. There isn't really a logical reason for why it is. So anyway, polypropylene, right? So you have polyethylene, polypropylene, the 80% of the plastics of those materials, right? Now all the polypropylene that you get, so like if you have a milk jug, the base of it is polyethylene, high density polyethylene, and the lid is polypropylene. So like the jug itself is kind of more flexible and the lid is stiffer. So that's a little bit one of the differences between the two. So basically, polyethylene, like you're just Larry. Oh, sorry. Yeah. Polyethylene, like that kind of nomenclature is like these are carbons with hydrogens. You leave off the hydrogens, you just draw that stick figure. And then polypropylene is just stick a methyl group on the side. And then poly-1-butylene is like the same thing with a kind of like 2 on the side. Then sometimes you'll have copolymers. So you can have ethylene propylene copolymer, you can have ethylene propylene butylene copolymer. Or you can, so this would be like a comonomer. So this butylene's usually used as like a comonomer, not as a polymer in and of itself. I don't know why, maybe it's because it's more expensive. So you'll add in like comonomer butylene to get longer side chain branches, and then when this thing wants to crystallize, the polyethylene actually it's in a planar zigzag conformation with all the hydrogens. So if you kind of eyeball one of these bonds, so put an upside down eyeball here and look up that bond, then you have this carbon and that carbon. Then you can make one of the carbons a big circle, one a little circle, and each one of them has a 3-pronged thing sticking out. Let's call it Newman projection. two ends. Ejection. Right. So if you have you have the chain kind of on one of those. So the chain goes along. Then you have in polyethylene, you just have hydrogens in all these, so it's all the same, right? So when the chain goes over the chain, you get the high energy peak. You plot energy versus this bond rotation angle, and then when the chain is opposite, so when the hydrogens in the other chain, you get a lower energy peak. That's the three toggle switch of spinning around the carbon bond, right? You can kind of imagine spinning the top propeller. And then carbon over hydrogen is here, carbon over or chain over chain is here, and it goes back to chain over another hydrogen that's there. And the minimum of the toggle switches are there, and the best place, this would actually go trans, so it's actually totally opposite of each other. Let's call it trans. And the two toggle switches, so the trans is an absolute minimum, so that's a lower energy here. So the 0 points down here, so it's lower. That's the trans, and these are called gauche. So gauche plus, gauche minus, and that kind of toggle switching around. So it's like you turn the switch and it reaches a point. It's like really hard to turn it at one point, and then it goes down and it sits there, and then it's got another place where it can click easily, and another click easily, and then like hard to turn. So that's kind of what the whole chain is, and it's doing that, say 1,000 times along the chain, 1,000 of these toggle switches going all the time, and that's what gives it the conformation. And then you have to put on top of this like KT energy, that's what's available. So if this toggles above KT, it's unlikely that it'll happen. And then the probability of that happening would be like E over KT, E to the minus. So that's the probability that you're going to go over the toggle switch. And so it's kind of like you can figure out the entire chain using that let's go with Boltzmann probability, Boltzmann energy, right? The exponential. So if the temperature is really high, this thing's really small, and the probability is high, like 100%. The temperature drops, this number gets large, then you have a really small probability to turn the toggle. And so, and again, that thing, if you take ln of probability times KT, then you end up with like the entropy without the T. That's the entropy, SK ln P. So this equation is directly the Boltzmann entropy equation. Just take a log of it, take an exponential to two sides. Anyway, so we got that business. So that's all right. And then if you take two of these, this is one thing. So it can be trans gauche plus, gauche minus, and gauche plus and gauche minus is the same thing. Just depends on how you look at it. Like forwards, it's gauche plus. If you look at the other way, it'll be gauche minus. Right. So anyway, they have the same energy, so it doesn't matter. Right. So, and then all right. So that's one monomer. Like if you have, right. So the other, you can stick on the side of here CH3 if it's going to be polypropylene, right? And then the next one over is an H. So you have CH3 and H, and that's going to change this energy diagram of the thing, right? How it can flip. And then if you take two of these, then you have this issue. Like say you're going like this is the start and this is the finish, right? So you have a directionality to this. See, actually the dot should be the start and the other one should be the finish. It's easier for my brain to work on it. So you start with a chain here, then you're going to go down that way. Then you get to this bond, so you're going like down here, then you get to that bond, so you go into the projector. And then you get to this one, which has a methyl group on it, right? So once you get to that one, and you're going to go that way down that chain, you can either make it go to the right or to the left. Like I could put the methyl group here, or I could put the methyl group here, right? I have a choice to go right or left, right? That's called stereochemistry. Okay, like in other words, if you make this stuff, so if you do a chemical analysis, right and left, it's got the same chemistry. It's exactly the same material. So these are enantiomers, if I pronounced it right. They're like two things that have the same chemical composition, the same structure, but they're different. One's right-handed, one's left-handed, right? They're exactly the same thing. So anyway, so as you go down the chain, then the next one, you can choose right or left. So say you chose right for the first one. If the next one you choose left, that's called racemic. Right, so, and he calls it racemo. So I guess there's two ways to talk about this. Racemic.
Over a little bit.
Oh, sorry, I gotta zoom out. Okay, all right, so racemic comes from this, from racemic acid, which is like something like this. I think there's a carbon in the middle, and it goes another carbon, and the other carbon has another OH, and this thing has the ability to be. So the way it is naturally is that these are right and left hand. Like when you're going down that carbon-carbon bond, the two groups are identical on the two ends. It's a dicarboxylic acid. So you could polymerize this if you wanted. You could polymerize from that group and make a polyester. Anyway, but basically, it can have a handedness like right and left through this. In the natural form, okay, so race from Greek or something means grapes. Oh, it means cluster. Race means cluster in Greek. So this is an acid that comes from grapes, which are clustered. And the acid happens to be a mix of like right and left. So that's where the word racemic comes from. And the other case is if you have the same, so you do right, right, or left, left, right? And there's equal numbers because you can do left, right. So statistically, this all becomes like statistics. And this is going to be like a 50-50 mix if it's random. Okay, because it's just flip a coin, you did left, and just flip a coin at 50% would be left, 50% right. So, and if you did right, the same thing. Right? So it's always going to be a 50-50 mixture if it's random. Right. So if they're the same, so it's left, left, right, right, that's called meso. Right, which isn't, so the weird thing about these words is that they are from totally different origins. So like Mesoamerica is Central America, right? So meso means center, but it comes from the word of a reflection, you know. So it means that like you put a plane between the two and it reflects the same the two ways somehow. So somehow it means center and it has to do with being the same here. And racemic doesn't have anything to do with any logical sequence. It's just grape juice. It's like the acid in grape juice, which happens to be a mixed. So the origin of these two words, even though they look like the same, like meso, racemic, look like kind of the same. They must have the same origin, but they don't. So, anyway, so that's the beginning for it. And these things are called, if you have two of them, it's called a dyad. Right. So it'd be nice to know the dyad sequence, right? Unfortunately, there's no way to measure dyads. Like there's no analytic measurement of dyads. And the way that you measure this is you take the proton, so you have a group here, CH3, a group here, CH3, and then you have the hydrogens here, right? So you pick up the signal, so that hydrogen will be split by other hydrogens. The protons will be split by other protons. So you have a proton here, you have a proton here. And it depends on how electronegative those protons are. So having a methyl group here draws electrons away from that proton. And that makes this proton split 4 times because they're different protons on this proton. So you end up with like a 4 split on that thing. I think it's too big and too small. So if it's just the proton, you get 1 peak. If they're split that way, depending on if they're different, if these two are different, you get 4. So if it's a racemic triads, you have 1, 2, you have 3 units on this thing. So it's a triad. Then it'll split 4 times for racemic, and if it's the other one, if it's racemic, if it's racemic, if it's meso, so you have 2 units as 2 of these dyads make a triad. Then it's just going to be like 1 peak, or makes it into a doublet, I guess, for meso. Right, so you get wherever the resonance. So NanoMara, you're coming in with you put your sample in a big magnet, and the nuclear spins, which are usually random, align to a magnet. And then the energy it takes to make those pointing nuclear magnets tilt a little bit. So they're constantly processing, and when they tilt a little bit, is the energy of a radio wave, like WLW will make that thing flip, right? But Ordinarily, it doesn't matter because they're randomly pointing around and the radio waves are hitting them and they're constantly just getting kicked around by that too. But if you straighten them out and fix them like a guitar string, all of a sudden that radio wave makes it sing, makes it have a tune. And it'll precess back and forth. And that precession is also in the radio frequency. So it gives off WLW back to you. Right. So basically it's kind of a simple thing, but it's nuclear physics involved in it. So it's kind of really complicated and kind of really simple. It's just you put a big magnet on, make the guitar string sing, then you zap it with radio waves, and it makes it sing back to you, and you listen to what comes back. And what comes back is influenced by it absorbs at certain frequencies. Like this precession happens at certain frequencies, you get a really sharp spike in the signal. You get like nothing, then absolutely a huge spike. And the energy of it and the frequency where it happens are all deterministic. So you can calculate the entire NMR spectrum. You can get, and from that, you can get the entire, because of this influence of splittings from the other protons, then you can get the entire structure of the material from that. Like the topology of it, how it's put together, including the stereochemistry, right? So basically NMR, proton NMR is you can use other nuclei. So proton's one, carbon 13 is another one. So those are the two major ones that people use for hydrocarbons, right? So basically, anyway, so you can tell, and you can only measure triads because you're picking up a radio signal in the middle, and it involves 3 meridians to do that. So you have like dyads is really the stereochemical base unit, and then triads is 2 dyads. Then you can get pentads, which would be like R, 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 M, 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 M. And then you can have any combination like R, M, R, etc. So you can get quite detailed about the stereochemistry. And then you can get so triad, dyad, triad, pentad, heptad, nonad. You can keep going up in odd numbers because it has to be odd because you have to have the middle one and 2 on the side, or 3 on the side, or whatever you have on the sides. Right, so it always has to be an odd number.
The dyad is the base unit.
The dyad is the base unit, but you can't measure it. You can only measure a triad or higher odd collections. Okay, and if you're going to crystallize, which is the main point of understanding this, so you're going to have a chain, and it's going to be a 10 nanometer thick crystal, and you have 2.5 angstrom or 0.25 nanometer steps to it, right? So you have something like 40 units in it. So you need a 41 add, right, to figure out is it going to crystallize or not, which you can't get. I mean, the best you can get is like 11. And that's if you have a gigantic super magnet that you can't walk into the room on. Like if you wear your watch and you forget it, you're dead because you can't get it off the magnet. It's there permanently. And these magnets run, you don't turn them off once they start. So they just have to keep running. So you can't turn off the magnet. Yep.
What dictates if it's like a dyad or a triad or a?
I mean, they're all there. It's just a matter of like how many you're counting. So you're going to have 100 units, say, or 10,000, just when you first start to get entanglements. So you got 100 units. So really a 99 at is what you're talking about with the whole chain. You want to say everything that was there, but the most you can get is maybe like 9, 11. Right. So you can tell kind of chunks of it. And then from that, you could maybe think about how that's working, Anyway, isotactic polypropylene is almost pure 100% meso. So always on the same side. So always with the same handedness, like right, or left. So it just depends on which, if you start from the one end, it's right, the other end is left. Right, so it all becomes like a statistical thing. Like you say, you're going to have, so you can have, if you want to have a dyad, you can have MR, RM, you can have RR, and you can have MM. Right, so meso is called isotactic because iso means same, so it's always on the same side. Right, that one's easy. And RR is switch, it means they switch every time. So it's right, left. So it's called syndiotactic. And then MR means you have right, left, or left, right. So you have, if you want to do it like that, it's like that, or like that. Right, and there's 2 ways to do that. You do MR or RM. So that means if you have a random mixture, there's 50% hetero, It's called heterotactic. And that's going to be 25% syndiotactic and 25% isotactic for a random mixture, which is kind of called atactic. So usually you'll see, like for polypropylene, you can buy syndiotactic, almost all of it is isotactic, and you can make what they call atactic, right? So you think like it's exactly the same chemical composition. It's like the melting point would be the same temperature, and the glass transition would be the same. But the glass transition between iso and syndio is like 80 degrees different. It's exactly the same material, absolutely totally different behavior, right? And the crystallization point shifts by like 30 or something, I think, for polypropylene. So it's like, it's kind of weird, but no difference at all, except handedness can completely change what the stuff is. You know, so you think like this is an incidental minor issue, but it's actually pretty major, you know, for depending on. So this is only going to be when you have a change, like polyethylene doesn't have tacticity because it's all H. So there's no tacticity. Right. So one of the main consequences is that they make helices. When you have this regular stereochemistry, they'll make a helix. Right. So the different tacticities have different helical, and the helices have different persistence. And the persistence you measure is really the helical persistence of the thing. So polyethylene has absolutely the simplest helix. It's a planar zigzag. So it's just like when you draw it on the board, it's just like that. That's the trans conformation where these side groups are opposite each other. And things that's got a really actually a pretty high persistence. Right. And then the isotactic polypropylene have, I think it's called a 4-1 helix. It's like how many turns per something. So you count how many loops you have per repeat unit or something like per the structure repeating. You know. I think it's something like 4-1. So you have like 4 loops to when you get back to the start point on it. And then that's got a lower persistence than polyethylene. So he's got in here. So he's measuring the persistence length in a simulation versus the position along the chain. So you start at the 0 point, go to the end point. And then he's got black is polyethylene. Oh, sorry. Yeah. All right. So black is polyethylene, and then it's at the top. He's got the highest, and then he's got syndiotactic polypropylene's red, isotactic polypropylene's way down here. Right, so there's quite a bit of difference in persistence. It's going from, this is like 0.7 nanometers, and then syndiotactic's like 1.3, and then the polyethylene's 1.5. Right, and then he does this trick, like, so he says, oh, it's not going to be all iso, and this is a syndiotac. It's not going to be all syndiotac, and that's going to be all. It's going to have some like random things kicked in. So he randomly kicks some things in. Then he can measure the persistence for each unit here. What he finds out is that he gets this green curve. So like for this green thing where he's got isotactic and he's thrown in some syndiotactics in there. And then he gets these like jolts in the thing. Yeah.
When he's describing the persistence of the conformations, is that separate from the persistence length that we've been talking about?
The persistence length would be like a mean value for this entire thing. So you can see the N groups have a significant contribution to it. In fact, it goes like to 0 for some of these. I guess polyethylene doesn't, but it should go to 0 at the N group. And then it's got a, if you have a high enough molecular weight, it reaches a plateau. So if you don't have a high molecular weight, you never reach the plateau. So the number isn't really kind of physically significant, I guess. Mm-hmm. This is going after 20 units. He starts to see a plateau in it. So polyethylene's 14. So that'd be 2,800 grams per mole for 28. Right. So if you have less than 2,800 grams per mole, you don't see a real persistence show off.
To backtrack a little bit, what was the difference between heterotactic and atactic?
So hetero, all right, so if you look at it like racemic meso, so RM, so hetero is RM or EMR. And then so in terms of sticking things off the side of it, it's like 2 go one way and 1 goes the other. And then syndio will be like up, down, up. And then iso will be up, 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 or down, down, down. And syndio could also be down, up, down. So there's 2 of each of the iso and syndios and 4 of the heteros, because you could do up, down, down, up, up, down, 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 up.
That's with like the bonds, like going down, down, down.
It's a handedness going, but usually it's drawn like he'll like, all right, so he doesn't bother drawing it because that's really wrong to talk about the direction, because they're all going in the same direction. They're all exactly the same. It's just like my left and right hand are the same roughly. You know, so basically, neither one is pointing up or down. I mean, I can flip them and make them point whichever way I want. It's just that one's left and one's right, and they aren't the same, right? They're stereochemically different. So he shows, it's nice how he does, he just shows a bar, he says blue is iso, then white is blue is meso and white is racemic. He just shows it like that, so you don't have to worry about like which way things are pointing. He does draw a picture of the chain that kind of shows which way things are pointing, but so anyway, so it's a little confusing, like there's a lot of, so the easiest way to draw it makes it wrong, you know. The easiest way to draw it is just say like up, down, up, down. But you have to realize that isn't anything like what it is, because my hands aren't going up and down, they're like two different hands. I mean, they're exactly the same, but different. All right, so that's about that business. Then, so he's going to do a computer simulation. So he's saying that the fact that you can get chain density, so he wants to get the chains packed together, not just one chain. So he's going to take like 50 chains, and then he's going to get these numbers by averaging the persistence for, so he has the unit sequences. So all 50 chains, he can address like which position it is on the chain. So he can get the persistence for like that unit on 50 chains and average it in his melt, you know. And the normal way to do this that was done before this is to take one chain and just look at the structure that you get out of it. So that was done by these guys and some other people too, like these guys and also these guys, right? They both did that. So they do it using a different method. They use Monte Carlo. So they take so they have the toggle switch going down. They know the energy, so they can calculate the energy for one chain, for the whole chain, by summing up all these toggle switches and the energy of rotation for the things. In other words, when it's at the peak of that energy plot for the humps, then that's a high energy, and then in the valleys, it's a low energy. There's two lows, right? So you can make this whole thing into a toggle switch game where you just randomly flip the toggle switches, and then you say, randomly flip them, and then say like, what's the energy of the chain? And then go, so you start with the chain one set, get the energy, randomly flip them, get the energy for the chain. So sum up these toggle switch energies. And then if it's lower, that's good, I accept that, that's good. But sometimes they say, well, if it's higher, then I'm gonna take the exponential of that energy, like a Boltzmann factor of that energy, Boltzmann probability for that energy, like exponential minus that energy over KT, give me a probability 0 to 1. And then you're going to flip a coin and say, like, if that probability is higher than whatever I flipped, there's a random number generated from 0 to 1. If the thing, my energy's difference, so delta E over KT is bigger than the probability that I randomly got, then I'll accept it, even though it's a worse energy for the whole system. And that allows you to get over like energy barriers. That's called Monte Carlo. So the Monte Carlo part is flipping a coin or find a random number. And it's called the Metropolis Monte Carlo. Metropolis was a Greek guy that invented this method to do simulations. So that's a pretty common way to do this kind of problem. They're going to do a flip coin and then let it do that like a billion times, you know, and then find out when the overall energy is going to go up high and it's going to like plateau out at some point. When energy reaches a step, I'm done then. I say like I'm finished, and that's going to be the confirmation of the chain, right? So then, and at that point, I can go in, and then all these guys do the same thing. And these are the people that invented this method. But the method is to go in and use this equation, which is that you have the chain end-to-end distance, and then the dot product with the normalized direction. So the end-to-end distance has a direction, and then so this is like the sum of all the R vectors in the chain which on average would go to 0, but for a given chain, it has a direction to it for the chain. Like you take the beginning and the end, there's an arrow between them, right? And every unit is pointing, every mirror unit is pointing in some direction. So you do a cosine, this would be like the cosine of the angle between those two directions. And then this is 1, so you make that unity. And then you have the length of the chain, so that it's going to be some fraction of the chain for every unit. And if you sum up all those, I mean, take the average of every one on the chain, then you end up with a persistence length. So you have to do a little bit of mental calisthenics to figure out why that is, but it turns out it is. These guys explain like why it is. So this Kurt Bender's is like one of the seminal polymer guys in Germany. All three of these people are pretty famous guys, and this Max Planck Institute's the top polymer place in the world. It's in Germany. It's in the like Frankfurt and Mainz, and in between them is where BASF, the original BASF, right, which was like the largest chemical company in the world by order of magnitude before World War II. Then after World War II, it broke apart into all these other companies. BASF still exists, but now at this point, if you go from Frankfurt to Mainz along the Main River, like chemical plant, chemical plant, chemical plant all the way, you know, and it was originally dye, and the river would change color when they had made different dyes than originally, like in the 1950s or something, right? So anyway, so they stopped doing that, but basically like Evonik is upriver a little bit from that. So every chemical plant in Germany is along that river. You know, it's like a fairly small river, and it empties into the Rhine at Mainz. And that goes to the Netherlands, and they can ship to the world from there. So it's kind of like the muscle of Germany there. But anyway, so Mainz is like the capital of polymers in Germany. There's two places now. There's Dresden and Mainz. And Dresden, when West Germany, East Germany merged, the wall fell. Then they felt like they had to like dump more science into East Germany. So Dresden, this Dresden Helmholtz Institute is another place now, but it's mostly, Mainz is still like the traditional, kind of like the Harvard of polymers in Germany, more or less. It's like right in the middle of where all the work is done. Right, so they came up with that. They came up with this equation, and one of the questions is like, explain this or something, like look at this a little bit. So maybe you can do that. Anyway, so that's how these things are calculated. So they calculate it for each position, then you can get these curves. Then you can see the end groups are more flexible, and this changes with tacticity of the chains. And also there's these weird blips on the thing. So they analyze like in detail some of these blips, like what's going on. So anyway, so one way they do it is they say this is a time dependence, and the simulation goes 160 nano. Doesn't sound like long, but it is actually really long for a simulation. This is all the chain units up to whatever 100 chain units on a chain. And they look at how thermally these toggle switches are flipping, right? So just looking at it. And then these are, I think it's like dihedral. This is measuring the dihedral angle. Okay, so straight off, you can see that the syndiotactic has a lot more consistency through it. It doesn't flip as much as the isotactic on the top. And this, I think, is syndio with an iso, or this is iso with a syndio stuck in it, the one syndio unit. You can see it shows a chain over here. So that one unit is stiffer, like less flippy than the other ones. That's kind of the point of this. So it's interesting how they did that. Dihedral angle. So he's doing a simulation. He's not using Monte Carlo. He's using molecular dynamics, which means like you take the particles, you put them in positions, you give each one a velocity. So at the beginning, then you say go, and just let it run on its own. And then the particles are going to move around. They're going to hit each other. So they're going to have momentum, velocity, acceleration, and they're going to interactions that they have with each other. Just let it happen. Right, and then you look at the density of the system and the temperature, and you try to get it to like come down so it reaches a constant value, then you kind of die. You reach equilibrium. So molecular dynamics is going to rely on a series of equations for energy. So he's using all right. So, and he wants to get how the relative angles of the units are with each other. So normally you'd use a program called LAMPS. which is like from Sandia National Lab, to do this kind of thing, right? But because he wants these angles, that angle concept is more akin to biology, where you have proteins. You're going to model proteins. Then you have a thing called dihedral, the two dihedral angles. Okay, so he uses GROMACS, which is a program that's designed for biology, really, because you would never see dihedral angle in lamps. I mean, it wouldn't. I mean, you could maybe get it, but it's not natural to get it there. Right, so these are like packages. They're free to use. You can just download them on your PC and run stuff on it. And then if your problem gets bigger and bigger, then you need a bigger computer to do it. So anyway, he's using GROMACS. So this is the web page for GROMACS. You can look at it if you want. And you can find where people have used it. You can get the code for different things that people do in it. But one of the, so you get, normally for proteins, you get this dihedral angle. So anyway, this is a protein. So it's basically, it's got a peptide bond in it. So you have carboxyl group, carbon and oxygen, double bond, you have kind of an amine group, nitrogen, hydrogen, right? And then you have a carbon, right? So the carbon attached to it is some group that changes. So all the proteins are the same, except that this R group changes. Right, so it could have like a sulfur on it, and then you get like a disulfide bond that will stick together to link it together. You can have a hydrophobic group, hydrophilic group, you can have polar groups, right? So I think there's 16 or something. I forget how many amino acids there are. But anyway, all the proteins are going to be made up of these things, right, in different sequences. So this double bond has a resonance structure. So basically, the electron here, half the time can spend over here and make a double bond between carbon and nitrogen, right? And then it can pop back. When it does that, then you get a negative charge on the oxygen plus on the nitrogen, right? Because you have that resonance structure, that makes an sp2 bond, which is a in planar bond, which means both this and that are planar, and they're coplanar. In other words, the bonds for this carbon atom are going to be like 3 directions on a plane. And for this nitrogen, because it's also got sp2 once in a while, will also be coplanar. So this whole thing from this alpha carbon to that hydrogen, to that alpha carbon, to that oxygen are all like a card in plane deck, right? And then at the edge of the card, they're hooked together, there's a carbon there, right? So you have these two cards like that, okay? So they call it like in airplanes, they have dihedral angle. It's like the two wings of the airplane and kind of how their angles are to each other, So the dihedral angle means like, hedral means face, like polyhedron is like the face of a cube or something. So it's like dihedral means two faces, and it's the angle, this angle of the two faces relative to each other, right? So it's really like, there's really like 3 dihedral angles. There's like psi, phi, and omega, but the omega is always, these are all coplanar, so the omega is like a fixed number, right? So you have a fixed number for the middle one, and then you have psi and phi. So you can see it kind of looks a little bit like stereochemistry, but it's not exactly the same thing at all. So he's using the nomenclature, but there's no planes in the polypropylene. So there's no dihedral because there's no faces to orient. Like in other words, it's dihedral because there's 2 planes and the angle between them. So wait, you can use the same program though. And if you look, like usually you'll see this, I forget the name of this, but there's a projection of the phi and the psi angles, or Ramachandran plot, it says right here. So the projection of those will tell you, you can see these angles. So this is for a whole protein, you just plot every one of the MERS in it, of the dihedral angles, just throw them on a scatter plot. You find they group up. So they group up into alpha helices and beta sheets. So the 2 main features in protein. So when you display a protein, you're gonna use, like, instead of showing the chemical units, you're just gonna show a helix. Alpha helix can be like plus and minus. So plus and minus alpha helices will be in different kind of quadrants of this thing. And then the beta sheets are like these sheet structures. So when you denature a protein, and then it refolds. So denatured means you pull it apart into a string, and then it folds back. So So this happens in the human body too, is cataracts are caused by this. So they fold back, so UV comes in, blasts the proteins in your lens, cooks them, and then they kind of refold into these beta sheets that make fibers. And the fibers make like amyloid fibers, or what makes your lenses go white if you spend too much time in UV. Right, so and there's a bunch of other diseases like that. So basically the generic thing when you mess with a protein is to make these sheets, these beta sheets, and the beta sheets are like have a certain phi signature to them. Right, so you can take any protein and you can make this map and you kind of say what fraction of it is alpha. Anyway, so the proteins, there's a lot to proteins. You can download this protein data bank. You see PDB files, and then you can find any protein. Like I was looking at lipoprotein A, right? So you just put it in whatever protein you want, and it'll find it if you're lucky, if it loads the data. And then then you can get this PDB file, which is just like tells, so it just, I don't see exactly it here. This is the thing that causes heart disease, this protein, but so you go here and you can download the structure of it. So these have all been measured by X-ray diffraction, protein crystallography, and then or by NMR. Like they use NMR to figure out these structures too. The same thing about the splitting the peak thing. Anyway, so you click here somewhere. Let's see. All right, you click somewhere to get this thing. Supposedly, like if you get a high level of this protein, so 20% of the people have a high level of this protein. And then you can see that structure, right? So it's got, these are beta sheets. And then there's an alpha helix right here. There's another alpha helix here, right? So usually you just, and then the rest of it is kind of nondescript. Actually, the rest of it that isn't alpha helix and beta sheet is the functional part that actually does whatever it does to give you heart disease. Like it binds with lysine or something, and then somehow makes calcium deposit and kill you. You know, eventually, over time, you know. So people study these proteins to make drugs, and then they can sell the drug for a huge amount of money. Or they make something that will block that binding site, right? And that's kind of the game of making new drugs. Anyway, so this field was like pretty hot for a long time, and it kind of died, and now I think it's kind of coming back a little bit. It's kind of had ups and downs. Like a bunch of people are trained in this. So where is it that you get the PDF file, download files? PDB, protein DB, CIF. It can be any of these formats, I think. And then you can read it into this program. You can. This is a web program, but if I can find where that file went, it's probably in downloads. Right here. And you open that, and then you have to display it somewhere here. There's a bunch of these you can download. There's like PyMol is one that you can download for your computer to look at the proteins. I don't know. It's fun to mess around with this, I think, if you have time, but maybe apply. There. So it just shows you, and this is 3D, you can mess around with it. Right. And then you can, so any protein you want, you can get in the protein data bank. There's literally something like 1 million, and more than 1 million proteins have been analyzed because there's so much money. And so you see the alpha helix of beta sheets. Anyway, so you can mess around with that if you want, but he's done that. He's taken that and gone to the simulations, and then, so he's talking about the dihedral angles. He maps them out here. And then he does this Ramachandran plots of this thing, and he says these are left and right, left and right helices. So this 4-1 helix for polypropylene, it can be handed also. Like you know how you have reverse screws? So you have a screw that turns left instead of right to tighten, like a security screw or something like that sometimes. Anyway, so same way with alpha helix, you can go left or right. So he figures out like he can get a mapping of the entire protein by these dihedral angles within which it isn't exactly the same dihedrals. Like there's only 2 angles in this, whereas in the protein there's actually 3. The third one's fixed. Right? So anyway, and then across the middle, he says what these are. Right, so we can map out with the positions along the chain, how this dihedral stuff works, this is a pretty nifty thing. No one else has done this. This is the first time I think anyone's looked at synthetic polymers using dihedral angles like this. So I think it's kind of an important paper, and so he talks about some features of the chain that way. Calculates the characteristic ratio for a comparison. So he calculates this so we can compare it with this paper where they didn't do dihedral angles. They just have that plot, right? This is the earlier paper using Monte Carlo with single chains. So they got syndiopropylene is 11 CN. So this is the ratio between the Kuhn length and the chemical unit length. And then polyethylene is 8.5. So if you go back to our guy, he's got, let's see, he doesn't have polyethylene. He has propylene, isotactic polypropylene. Let's see, somewhere he does this, the whole group of these, I think. But anyway, so you can compare those two papers. You'll find out that the trends are the same. Like the syndiotactic has much more persistence than the iso, but the numbers are different. Like they get different values. So that makes you kind of wonder how accurate these things are. I think there's another one of these C-infinity plots in here. I don't see it right now. There's two of them, but one's directly exactly the same as this plot. And it looks the same, but the numbers are different. And then what else is in here? I think that's about it. So it's pretty interesting. It's a pretty good paper. So he calculates, once he has the chain, he can do a Fourier transform of it and get the scattering from it, which is kind of common. And then he looks at the scattering, and you can get the persistence length from the scattering curve. So before you transform a structure, you get what you get from small angle scattering, like intensity versus Q. He multiplies that by, because it should be a power 1 minus 1. So if you should be S of Q equals Q to the minus 1. So if you multiply it by Q, this should be a constant value when you get to the 1D part, the rod part. And he says, oh, it goes 1D here. That's 2 pi over that Q is my persistence length. That's one way to get the persistence length from the scattering measurement. So dimensional analysis. And what else does he do? He does a lot. Like I didn't even like this is trans-gauche. This is kind of the probability, the Boltzmann probability trans-gauche thing. It's a lot in here. This plot, I don't remember exactly what he talks about this plot too, but wait, let me go through the questions as quick as I can here. So tacticity, NMR, blah, blah, blah. For a description of persistence, why would the optimal number of Murray unit, what would be the optimal number? So that depends what you're interested in. Like in other words, dyad, is that good enough? Probably not. Triad, is that good enough? And triads are normal to say like isotactic polypropylene, but that doesn't tell you really anything. Because if it's 1,000 units long, you know about 3 unit groupings. So and you can see like if you throw one monkey wrench into it, it changes the whole thing. That's kind of the point of this paper, right? So anyway, basically you need at least, if you're talking about 10 nanometers, whatever I said, like 40, you need 40. That's going to be the thickness of a crystal. So if you have to have 40 across the crystal, if you have any kind of deviation in that, it won't crystallize. If you have iso, syndio, and then 30 more isos, that won't crystallize. So one monkey wrench will ruin it. So that means you can only make the 30 thick crystal. That means it's going to have a lower melting point. It'll be gooier, right? So it changes the material.
You're saying the optimal number of Murray units to look at depends on the purpose of why you're
Exactly. Yeah, and it's going to be much more than a triad, no matter what you're looking at. It's going to be in the close to 100, So it's basically not achievable. So the only thing that tacticity can give you is like an inkling about what's going on. Simulations can give you the whole thing. They can give you anything you want. Any question you ask, they can answer. Whether it means anything is another story, but basically it's possible to get any answer from it. Then this thing is just a bunch of questions about the simulation method, fixing to achieve, da, 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 da. This is where, da, 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 blah, 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 blah. Chen uses, let's see. So for MD, there's some questions at the end of this. Dihedral, common, described present alpha. Chen uses blah, blah, blah. Oh, explain here, how can cutoff distance speed up the simulation? Okay, so he's got a thing called a OPLS function. All right, I gotta say something about that. So this is where you're gonna throw everything in, you're gonna give it some rules. And then that's a good thing too, but where's the OPLS thing? Guess I didn't open it. Chromax Binder. Oh, I think you just have to Google it, like. So this is it. So these are the rules that he's gonna go by. So he has, this is like a spring constant. So he's got force, force is the spring constant times the distance. You take a spring, you pull it, so force times distance is linear. So if you integrate force with distance, you get distance squared times the spring constant gives you a spring energy. So the standard thing in these is going to be like a spring. So the bonds are like a spring with a spring constant. The twisting of the bonds is also a spring. So it's also got square to the kind of the length part of it, and it's got a twisting constant. That gives another energy. Then this is the dihedral part. So this is however the dihedral twisting affects the energy. So I don't know where this function comes from, but basically it's some kind of dihedral function. And then this is a 612 potential for repulsive and attractive interaction. And then this is a charge you throw in because proteins can be charged. So you have a charge component. This number would be 0 for us. Like there's no charge. So we just have a 612 potential for polypropylene. Right, so this is set up for biology. It's built into the GROMACS. Those are the components and typical of what you'd get for interactions. So it's includes both conformational energy of the thing changing and also interaction energies, right? And then you just throw that in. You say you have a bunch of things which you're going to call atoms. So he calls it whole atom. So it's saying these are atoms. When they follow this potential, you get parameters for those from the atoms that are there, and then the bonds that are there, and you just let it cook. You just let it do anything it wants. It's going to just knock around, and eventually you're observing, like, if you sum up all the kinetic mv 1/2 mv squared kinetic energy equals kT, the temperature. So you map out how the energy changes with time as that thing cooks on its own. Then finally it'll plateau out, and boom, you're done. That's when you're finished, right? So it's like just let it cook. There's no rules. It's a free for all. Let the thing decide for itself what's going to happen. You give it the rules, it decides. You know, that's the dynamics, and those are the rules. Anyway, so that you have to Google. That's about the energy, Leonard Jones. Oh, here, there's a link here. Sorry. How can a cutoff distance? So basically, these energies are going to be acting out. So if you say R can go to the entire system worth, then that's going to be a lot of calculations. You have to calculate every R for like the 612. So you say like, I'm only going to have 612 over like 1 nanometer. That's it. I'm not going to look beyond that. So there's always like a cutoff distance to make it go faster. Otherwise it would take forever, right? So he's got that business, cutoff distance, and then this leapfrog algorithm, you got to watch the video, this guy that talks about it. And then, oh no, method of steepest descent. There's a video from the guy from Purdue that talks about it. Leapfrog, there's a link that tells you how to do that. It's basically, anyway, it's a little complicated. It's not that complicated. And then what is a canonical ensemble? So this is a lot of stuff to learn here, I think. But basically, there's different kinds of ensembles. So canonical is with constant. You fix the temperature for the system. So it's constant number of things in it, constant temperature, constant volume. And then that's a canonical ensemble. And there's different ensembles. There's a web page that talks about the different ensembles. Does a pretty good job of it personally. But anyway, equation 1, I talked about that a little bit. And compare the two figures, the C and C characteristic ratio from the two papers, and then compare the two simulations that they came from. And then he's talking about dihedral pairs. So just say what a dihedral angle is. The change and how it changes with just say something about it. There's a little bit, whatever I said about the dihedral angle plots. So it's kind of like a lot, this doesn't even cover the whole paper, actually. Like the questions only go up to about half-life. So, because there's only 5 questions, so, but hopefully. You might have problems with this, just email me and I can kind of tell you, how to do it more. If there's questions on Monday, I can go through them too, but. So why don't we leave it there and you guys can look at it. Yeah.
I think really good. For separation.
I really, I like to very
Like, what is that?
I think that's a very
That's not wonderful.
I can believe this.
Honor, oftentimes.